Thanks. Well, welcome back. That's the last lecture of Thierry. And let's see how we prove better energy estimates.
Thank you very much. So thanks for coming back to this lecture. So yesterday we have a TAF lecture. I mean, I tried to give a quite detailed proof of one of the main results. And today I will add a few comments to what we did yesterday, for instance, to see how to remove a strong limitation in the argument. And then I'll state and prove a variant of the result which concerns a slightly ill-prepared initial data. So, but I need to recall a little bit where we are, which will be useful for me and probably for you. So the equation we consider is the same as for the beginning. So dp omega plus v plus f calculated omega. If we go to the new direction of this problem, the vorticity equation for a vortex, which is affected by its own velocity field, like in this code, plus an external field f, which is supposed to be smooth, even, bounded, and etc. Okay, and the singularity in the problem is that at time zero, I consider singular initial data. So in this part, just again, I answer it somewhere. Gamma is the intensity, Z0 is the original position of the ball. So I explained that, so this was what I call this vorticity equation with external. So the first step was in the proof was to introduce self-similar variables. So we look for solution in the form gamma of mu t times some new function omega of x minus z of t or square root of mu t and t. This allows to desingularize the problem at initial time and near initial time. So this is absolutely necessary. And this leads to an evolution equation for the new omega, the new vorticity, the new variable. So which is t dt capital omega plus 1 over delta u. So it's the capital U plus e of 3 omega is equal to L omega. And this is what I call this omega equation. So there is some notation. I will not record everything, but I record that there are small parameters in the problem. Delta was mu over gamma. This was the inverse Reynolds number, because it is small. And there will be small an epsilon, which depends on t, which is square root of mu t divided by d, which is the active ratio, which is supposed to be also small. These are the main parameters I consider. Now, what is E? I will need the expression for E. So E is the influence of the external field in self-similar variable. It was given by an interesting expression. E of phi t would be something like epsilon T0 over E times F of C of t plus epsilon d psi at time t minus c phi of t. So from this formula, you see that E is of size at least epsilon. But if you choose d phi of t in a clever way, you can have partial consolidation here. And this start at order epsilon square, which is good because it's divided by delta in the equation, and epsilon square over delta is a reasonable quantity as nu goes to 0. Okay, now to solve this problem, the technique was to construct an approximate solution and then consider the equation for the remainder. So I will not repeat anything about the construction of the approximate solution because it was yesterday. So omega, we look for a solution of the form omega at psi t as some approximate solution, which was constructed as a finite power series in epsilon, plus a remainder, which is small, which is supposed to be small. So I multiply it by delta to be sure that it will be really very small. And now I look for the equation for this remainder one here, and this is the last equation that we have here. So it's E dt W plus 1 over delta lambda W. Lambda is a skew symmetric operator obtained by the linearization of Euler at the vortex. Plus there was some a little bit milder attraction term which I did not find. A of W, plus there was the nonlinearity which I told by quadratic form E of W. And this is L of W. L is, I didn't repeat, so this is diffusion operator in the self-similar variable. And then I have a source term, which is 1 over delta square times R up, and R up is the residue, the remainder of the approximate solution, which measure by how much this approximate solution fails to be an exact solution of the problem. So here we have to solve this with at time 0 initial data, because omega r and capital omega have the same initial data, namely the Ozane vortex, which I denoted by omega 0. So you solve this equation, you have 0 initial data, we can hope that the solution will be small for some time. You have a source term which is small if you constructed a sufficiently accurate approximation. This was the rule of the game. So the source term, even though it's divided by delta square, will be small if we can have a sufficiently precise approximate solution. And then the only thing that we have to treat is to make energy estimates on this equation, which I denote by W equation, in such a way that the dangerous terms that you have here do not destroy everything. Okay? So we want to construct the control this on a finite time interval, 0 T less than capital T. Capital T is fixed and independent of the viscosity, independent of it. So to control this, we use energy estimates, and let me repeat how it goes. Energy estimates. So what we did so far was the naive choice. It will be an improved choice in a minute, but for the moment it's a naive choice. We said, oh, okay, we shall take an energy functional P of W, which is just, we take away P of psi, which is E to the psi square over 4. And we define this as the integral over R2 of this wave T of psi times W of psi squared psi. And this is also the norm of W in the function space, which are denoted by Y. This was the function space in which the diffusion operator set adjoint and the advection operator lambda is Q adjoint. Okay, because it's miracle of space. And the natural choice is you take this one, and then we have the H1 version of this, which is important in the statement of the result, which is integral of R2 of P times gradient of W squared plus psi square W square plus W square psi. Obviously, this is larger than the L version, okay, because it contains in particular W. And then we have a proposition which I didn't state yesterday, but I more or less prove it technically at the end of the lecture, which tells you that there exists positive constants kappa and C, such that if you define W solve this equation here, and if you define this energy functional, then you have a differential inequality for the energy E. Okay? And this differential inequality reads as follows: E dt E of W plus twice times kappa minus T over T0. So capital T0, I repeat, was defined as 1 over capital T0 will be the supremum of the gradient of F. It's the characteristic time defined by the external field, which I argued is the time on which something interesting happens in the dynamics of the external field. So I have here F W, okay, is less than this constant times T over T0 times E of W plus a constant times F of W to the power of 1/2 E of W plus a constant times epsilon 5 of delta square plus epsilon square. So this is what you obtain if you do the calculation I sketched at the end of the last lecture. So let me repeat which terms here comes from what in the equation, because this will be important for continuing the discussion. So the time, okay, this is just obtained by multiplying the equation by W and taking the scalar product of the equation in my function space Y with W and estimating the values. So you see that you have good term here, K times F of W is good because the left-hand side is positive coefficient. And this K here is more or less the spectral gap associated with this linear operator. We should recall that integral of W is equal to 0. So L and the spectral gap, and this constant K here is explicit and related to the spectral gap of L. You can need something like 1/8 or 1/16, some positive constant. And now we have here a very bad term which has the wrong sign, but you multiply by T/T0. And this one is produced by, in this term here, the contribution of this E of the external field. Curiously, it's not the self-interaction of the vortex that creates the problem. This term here comes from the effect of the external field. I will explain. Then you have all the other terms like, so the lambda here gives no contribution by skew symmetry, and the other contribution from the affection terms can be summarized in this term. It's just T/T0 times E. This contribution here comes from the nonlinearity. These are standard estimates, this quadratic form. It's a linear term. You can estimate this by the usual estimate for Navier-Stokes. And this becomes nonlinear. So this term is not a problem because we will work under the assumption that the solution is small and prove a posteriori that this assumption is propagated. And this term can be included in the left-hand side with our info. And this comes from the remainder term. And the phi here is because we constructed a solution, approximate solution up to over 4. Therefore, the remainder is over 5. So this is what we chose. I mean, this remainder term can be what we want it to be if you construct the solution sufficiently approximate. Now, from this, we see that this gives theorem 2 if you assume, say, that capital T over capital T0 is less than, for instance, power K, because K over 2, because then this term is bounded from below by K or something like that. So this term is good. This one you could include into this if T over T0 is sufficiently small, but it's useless because we can just use on value inequality. It will just multiply anything by a constant. So you don't care about this term. This term you will assume that C times E of W to the power of 1/2 is less than, say, K over 2. Okay? Initially, this is true. As long as this is true, this term is less than K of 2 times F, so you can absorb it into the left-hand side. And you will see that this, of course, is propagated. The solution will satisfy this on the whole time interval. So no problem about the nonlinearity. It's just a question of assuming that. And this term we have seen is at least of order epsilon. So if you have this, you obtain that the norm of W of tau Y, which is this E of W of tau to the power of 1/2, is less than constant times epsilon 5 over delta square plus epsilon square. And this is certainly less than constant times epsilon. And this is enough to prove the statement of Stephen. But this is horrible because we see that the argument breaks down completely as soon as T is large compared to T0. And this is bad because T0 is the time scale on which something interesting can happen for the dynamic of cold vortices. If you consider the interaction of two or several vortices, it's typically the turnover time of this interaction. And it's very, very sad that we have to impose in this argument that T is small with respect to T0. So we would like to remove completely this restriction. And now I have to explain how this can be done. Is it okay? So this is what the point where we reached yesterday. And now I have to explain how to remove this condition. So to remove this condition, we must understand the origin of this condition. Okay? The origin of this condition is in the action of this advection term. So what are the dangerous advection terms? Let me give some naive explanation. So dangerous advection terms in the equations say it's these are the terms of the form 1 over delta times v dot gradient w, where v is, so you have, for instance, u0 or u approximation, but u0 is the most dangerous part, plus you have this e of, which depends on f and z, which is the quantity I equal to. So this one, u0 is, of course, everything is divided by delta, which is the big problem. So we have to understand exactly what we are doing. u0 is of order 1. This one is of order epsilon square, but epsilon square multiplied by psi. And we have seen yesterday in the calculation that this was a problem. This was the reason why it does not produce an E, but it produces an F. And F, you have only a finite quantity of this, so you cannot do whatever you want. Now, these are just advection terms. So what is the effect in an energy estimate? Suppose that you make an energy estimate with some weight P. So you will have something like integral of P times 1 over delta, P times W times 1 over delta, V dot gradient W. Whatever V is a divergence-free velocity field. This is the term that will be created in the energy, making the minus sign. Okay? The term that will be created in the energy estimate by the contribution of this term. And then you integrate by parts. So gradient of W times W is 1/2 gradient of W squared. Divergence of V is 0, so you can integrate by part. So this is exactly integral over R2, okay, of P, no, W squared V dot gradient of P inside. And there is the 1 delta also. So you have the 1 over delta, which is bad, and you obtain integral of W squared V dot grad V. This is what you obtain when you integrate by 1. And then you see what we can do. You would like this to be smaller, to be even 0. What does it mean that V dot grad V is 0? It means that the weight is constant under the integral curves generated by the streamlines generated by the vector field V. Okay, so to leading approximation, so far we are focused on our vector field being mainly U0. U0, I recall, this is a radially symmetric vortex, so the corresponding streamlines are concentric circles like that. Okay, that's the reason we took a radially symmetric way, because if it's radially symmetric, this term was 0. That's the reason why this, I mean, the advection part of this operator was too symmetric. It's exactly this calculation. Okay, but now we see that we have reached some limit, because when you do that, the mistake we did in this estimate is that we didn't take into account the fact that for a long time, this becomes a noticeable perturbation of this. You have to take this into account, not consider that your vector field is axisymmetric. So it's absolutely obvious what you have to do. You have to modify your way in such a way now that it is constant on the streamlines of this modified velocity field. So you have to take a slightly non-radially symmetric way in such a way that this quantity is 0 to leading order. Okay, so this is the improved choice. Okay, like choice, improved. Oh, I'm cheating because I know we cannot do that on paper, but okay, I'm modifying what I want. So now we should take another weight, P epsilon, which will be a weight. We take a weight in the energy estimate, which is P epsilon of psi and T. It will depend on epsilon and also explicitly on P. on G. So this becomes P epsilon, F epsilon. Everywhere it becomes P epsilon. And also the psi square I have here was related to the weight P before. So maybe I have to put some other function of psi here, which I will define. So we make a modification. Now we consider a different weight, which is no longer exactly radially symmetric. And we try to do the same energy estimate, but with this modified weight. And now I'll just explain you how to construct this weight. I already started explaining you how we construct, but now I will just devote a few minutes to do the construction of the weight. That's the price to pay. Not only you have to construct perturbatively an approximate solution, but now at the stage of the energy estimate, you also have to construct perturbatively a weight function. It happens that I don't know how to construct this weight globally in the whole space because the problems are different in different regions. So I have to separate different regions in my configuration space. And the most difficult part is the inner region near the position of the vortex. This is crucial. So I define an inner region of the following way. I'm giving myself positive numbers at A and B, satisfying A very small, B very large compared to 1. Okay? And I define the inner region by the psi which are less than A over epsilon. So this is an epsilon depending region in the self-similar coordinates, but if you go back to the original variables, it becomes fixed in time. So it's just the disk of radius A centered at the vortex in the original coordinate. In this region, I make the following choice. I define P epsilon as exponential of Q epsilon and chi epsilon of psi, the one that is in the functional F. I make the usual choice to be psi squared. This is what I had with the previous function. And what is Q epsilon? So Q epsilon of psi equals psi and T, and it also depends explicitly on time. So it was psi squared over 4. This was the choice I made so far. And now I add something, which is something like epsilon squared is 0 over 4 is 0 of psi. And then you have a stupid expression of the form P of T psi 1 square minus psi 2 square minus A of T times 2 psi 1 psi 2. And I don't repeat what is A of T and B of T are because I wrote already twice the expression. These are this combination of first order derivative of F, which enter the approximate solution and which are, okay, you have always the same quantity. And this is psi square cos 2 theta, and this is psi square sin 2 theta. So we get exactly the same expression, and in the expression of omega 2. I mean, the first order correction in my approximate solution. Okay, and what is V0 of psi? V0 of psi is 1 over 2 pi psi square is the angular velocity of the origin vortex into the minus psi square. Okay, so there are some explicit expression, which is a perturbation. I mean, in this region, this is a small perturbation of the previous one. You can see that this grows like psi square, but 1 over V0 also grows like psi square. So this grows like psi to the power 4, but with epsilon square in front, this term is a small correction to this one as long as A is very small. Okay, so in the region, in the some inner region, I can just modify the weight by some explicit formula. And then you have, by direct calculation, that the most dangerous advection term here just cancel in the sense that you have, if I make this calculation here, I have U0 the grad to epsilon plus epsilon square E2. So I recall that this quantity can be expanded in powers of epsilon. The first one is epsilon 2, okay, epsilon square. plus epsilon times the gradient of into 0 plus phi squared over 4. This is exactly 0. So these are the most dangerous terms. These are exactly the terms that produce this theory of T0. They cancel immediately. So we cured the problem. Now, of course, we made a lot of damage because now the weight is no longer radially symmetric. Therefore, this operator capital lambda will not be exactly symmetric anymore. And maybe the diffusion terms will be a little bit different. But all this can be cured by taking this A sufficiently small. If you make this modification in a sufficiently small neighborhood of the origin, which is still very large in my self-similar variable, okay, then you remove this term with theory of T0 and you add other terms, but they all have a factor A in front. In fact, I was missing a small parameter, which I didn't have. I have theory of T0 multiplied by 1, and I cannot make 1 small, but now everything will be multiplied by A. And then if this capital A is okay, is sufficiently small, then it's okay. Okay, so this is more or less what we do. I remove the difficulty due to a bad choice. The choice of my weight function was not adapted to the velocity field I am considering. So this is very standard. Now I have a problem because when I reach the boundary of this region, I cannot continue like that because this goes like psi to the power 4. So certainly at some point it will be completely different and there is absolutely no reason why this should work. So at some point you have to stop and you don't know what to do. So you should do a radical choice. You have to consider an intermediate region. This is very good though, but region. And the intermediate region is to assume that A over epsilon less than psi less than B over epsilon. So it's of order 1 over epsilon, but it's an analog between A and B. Okay? And in that case, we consider P epsilon to be constant. It will be epsilon exponential of A squared over 4 epsilon squared. We take it to be a constant in space. So then certainly I will have no problem with this integration by parts. If the weight is constant, all advection terms will give 0. Okay? Because it's advection by a divergence-free velocity field. It doesn't change the L2 norm and things like that. So certainly in this region, I have no problem. And the corresponding K epsilon should be also a constant with A squared over epsilon. Okay? But this is not good because I cannot stay constant until infinity. Otherwise, I will control just something like an L2 norm, and the L2 norm will not control the L1 norm and things like that. So I need to have a better norm at infinity. So I have a far field region now. Far field region, which is the last one, where psi is greater than B over epsilon. So here we take P epsilon to be exponential of gamma psi squared over 4, where gamma is A squared over B squared, and it's much less than 1. Then I take chi epsilon as gamma psi squared over 4. Okay, so it's again a Gaussian weight, but this Gaussian weight with a smaller weight. We have a smaller coefficient here. Why do I put a smaller coefficient? Because I need my weight to be continuous. So let me make the picture. This is the overall picture, cartoon picture of my weight. Okay, it's not completely radially symmetric, so it's a little bit cheating to write it as a function of modulus of psi. But what else can I do? So I have here A over epsilon. I have here B over epsilon. Okay, so here it's more or less the Gaussian, but it's not radially symmetric in this region. Then you have a long plateau, and then it starts again with something Gaussian. So this is my P epsilon of psi. It depends on time because the non-radially symmetric part here depends a little bit on time. So here it's exponential of A squared over 4 epsilon squared. Here is epsilon of exponential of gamma psi squared over 4. And here is approximately exponential of psi squared over 4, but there are additional corrections to it. And this all depends on time because it depends on epsilon. And now I have to put gamma here to be this, so that it is continuous, it's an increasing way. Okay. Why don't I have problem in the external region? So here I have something I forgot to explain. Because this quantity here can be bounded in two different ways. There is the one which used so far that we say that E of psi t is bounded by a constant, even the constant will be 1, epsilon squared times 1 plus psi. This is what we use in the inner region, and this is what this psi was the derivative of creating the problem here. Okay? So when psi is too large, you should not do that. But of course, you can also do a brutal bound where you don't take into account the fact that these two terms cancel. These are both bounded in N infinity, so it's also bounded by a constant like epsilon without any psi. And of course, this bound is better than this one when psi is very large. It's better by a factor 1 over beta, 1 over b, and b is large. Okay, so in fact, the term created by this E can be absorbed into this one as soon as B is sufficiently large. So in the exterior region, it's really dominated by diffusion. So here it's everything is dominated by diffusion. Here I have to do something very precise, and in the middle I don't know what to do, so I put a constant. Okay. So now you do that, and what happens? So it will be horribly cheating, but you obtain exactly the same differential inequality, except that there is a little modification here. You have K minus, you have some constant appearing eta in between this, and eta is order of A plus 1 over B. Isn't that nice? You obtain either an A or a 1 over B. Okay, so this T over T0 is bounded. It goes only to capital T over T0, which may be large, but it's fixed. Okay, and now you take A sufficiently small and B sufficiently large, and this eta will be sufficiently small so that we don't have any problem anymore. So we just have a little problem to cure, and it creates a lot of technical difficulties because the code is 3 times longer with this way than with the original way. You have to redo by hand a lot of estimates which were completely obvious in wise, but except from that, you have completely removed the problem. Okay, so this is what I wanted to say about the proof of theorem 2. Are there any questions? Yes?
Is the probability that depending on epsilon?
No, it's actually a constant that you can choose. It's depending, everything is depending, A and B depend only on the ratio capital T of T0 and the bound of F. So even, well, and we measure the bound on F in a way which depends on capital gamma. So gamma should be fixed also once and for all. Okay, so everything depends only on this one. Okay, so once you have this, you take universal constant depending only on that, and then it's true for all epsilon. So it's really 1 over epsilon, and here it's all, both regions are of this form 1 over epsilon.
And it was related to that. So there is no physical meaning like related to the vortex square like that. You're not looking into the vortex and not out the one.
Well, I mean, this interpretation tells you that in some neighborhood of the vortex, which is outside the order of 1 in the original variables, we have to make energy estimates to really take into account the deformation of the vortex. Then there is a region where it's not so important. And at the end, the direct diffusion will dominate all the regime, so it might be. Now, we can speculate. I mean, let me take 2 minutes for speculations. If you look at numerical simulations of a vortex pair, for instance, which is a case which could be treated with this method, you see that sometimes you have some filament of vorticity. When they start interacting, there's some filament of vorticity which are emitted. So a little quantity of vorticity which goes far away from the vortices. This is what you see typically, in particular when they merge, but also a little bit earlier. Okay, so this may indicate that you cannot measure the vorticity in a space for which the weight goes too rapidly at infinity, because otherwise this whole filament will give a strong contribution with that weight. So maybe we have, maybe we have to take a weight that goes more slowly at infinity, also so that these filaments of vorticity do not be too big with this weight. I don't know. I don't know if this is related, but it's not completely surprising. I mean, controlling with the weight e to the psi squared over 4 all the way to infinity is just neglecting potentially all emissions of filaments of vorticity, which may occur in the problem. So maybe it's not completely technical that we have to make a weight which goes in a slower way. I mean, extrapolating the weight here, if we continuing like this, maybe it's too much asking for the problem. Now, another comment is that this is a result in the philosophy where we take capital T fixed and we try to choose to go up to capital T independently of viscosity. There are situations, but not in that case, where we can go to capital T, which depends on viscosity and grows as the viscosity goes to 0. Okay, so not only a finite time interval, but something which grows. So in the general assumptions here, this is not written, but I think we could go probably to T to be log of 1 over delta, something like that, in general situation. But in particular situation, when you have some stability, we didn't put any assumption on the vector field F. It could generate a chaotic, it could be chaotic dynamical systems with sensitive dependence on the initial data and so on. And we put a vortex in that environment. So we can control on a finite time, but certainly not on a very long time. But now, if you assume that your F is independent of time, you have a fixed point which is stable at some point, and this is the place where you put your vortex, then you can go to a much larger time, which depend or which go to infinity as t goes to as the delta goes to 0. So some examples have been written. For instance, there is a preprint by me and Michele Dolce of last year for a vortex pair. In that case, we can go to a very long time scale. This was the talk of Michele on the Friday last Friday. But this was the philosophy, just a fixed time independent of viscosity, which is already not so easy if you assume that this fixed time can be done. Is it okay for now? So now I must proceed with the final result of this lecture, which is the case where we consider slightly different initial data. So let me explain what we can do. This is a modest result in the sense that it is far from the general properties we would like to establish, but this is what we have for the moment. So now, so this will be 4. And let me shoot un autre petit Python. Il prepare data. Okay, so what should we do? Let me do the following thing. We have the time interval 0 to capital T. I will be less and less precise and more pictures now. Okay. In the middle somewhere, you have this capital T0, which is the characteristic time, and typically the situation is like that. We took so far the initial data at 0, because of the Dirac mass. Now we will take non-trivial initial data, and to allow comparison, we chose them in the following way. We take some initial time T0 somewhere here, and we assume, so we consider, we fix, so we fix problems. We fix T0 in 0 capital T, no matter whether T0 is smaller or larger than capital T0, it doesn't play any role in the argument. And we consider the solution of my vorticity formulation with the F with initial data. So the initial data will not be at time 0, but at time T0, which is of course harmless, but I will explain why we do that. With initial data, so I assume that omega of x I times T0 is gamma over mu T0, capital omega 0 of x minus z0 over square root of mu T0 for some, we fix also z0 in R2, okay? And I recall that omega 0 of psi equal to pi of cosine vortex into the minus psi square over 4. So we choose to put our initial data at time t0 and consider the solution from t0 to capital T. Okay? And the initial data we choose are those ones. So Gaussian initial data. So the fact that we have this t0 is arbitrary. I mean, just say I fix some length scale L, which is square root of ut0, and I put consider as initial data a Gaussian vortex with typical size L located at Z0 somewhere. Okay. But we choose it to express in this way because we want to compare the solution with this initial data to the solution which starts from the Dirac mass H0, which is our reference solution we studied so far. And to allow this comparison, we chose it to consider the initial data at time t0. If you are skeptical, so I need some more explanation. So let me try to explain graphically what this means. I should convince you, so this is my role. If you're tired enough, it should be possible. So let me make a cartoon picture, or maybe let me state the theorem. So the statements are here for being read, and then we'll see what happens. Okay. So let me put a star here with this initial data, and let me at this stage the last theorem, so that I will be finished at least for the theorem. So theorem 3. You know the melody, I mean there exists a fixed, in the same theorem, fixed gamma positive, T0 in R2, and T0 in 0 capital T. There is an addition, now we fix also the initial time, okay? So there exists constants, K0 strictly positive. What was it? C0, no, it was delta 0, small, and now I have a C0 strictly positive, so I have an additional constant, such that if the Reynolds number is sufficiently large, so if mu is between 0 and gamma delta 0, the same assumption I made in the other theorem, the solution omega of xt of my vorticity equation with external field F with initial data star satisfies the following estimate. By the way, this is a regular Cauchy problem now, so I don't have problems with measure valued initial data, blah, blah, blah. I'm solving with smooth initial data, so at least I'm sure that there exists a solution, okay? So what I want is say something about the solution. So it satisfies the following estimates, 1 over gamma integral over R2. I compare omega of xt with, again, my approximate solution with circulation gamma, with length scale square root of mu t. So at initial time t0 is the same scale as the initial data. At the point z of t, with the external field f of t, evaluated at x, dx, and this is less than k0 times epsilon square times something. And here it was epsilon plus delta, you remember in theorem 2. Now it's more complicated. It's delta to the dot log, delta to the 1/6 log over 1 over delta to the power 1/2 plus small t0 of t to the power of beta. And this is for t0 t less than capital T. Where, okay, so epsilon I don't repeat, delta I don't repeat. And what is beta? Beta is a large exponent which is C0 delta to the power minus 1/3, and Z of t is the solution of the usual ODE, Z prime of T is equal to F of T of T. P plus mu T Laplacian of F of T of T. So the same as yesterday, with initial data Z of T0 equal minus T. So this is the last result I would like to say and to comment. Is the statement clear? So let me try to make a cartoon picture of what this theorem is meaning. So I draw a curve in the function space in which my solution is living. So so far we started at t is equal to 0 with some Dirac mass, so this is a dot. Okay. Now what happens at some intermediate time, which could be t0, then this no longer a Dirac mass, this was theorem 2. So it's something which is like an Ausen vortex, but some deformation of the streamline. So with some exaggeration, let me write this, I write some elliptic vortex here, okay? And this is just saying, okay, it became something with some extension and some eccentricity of the streamlines, okay? This is exaggerated certainly with respect to the theorem, but anyway. And at finite time, so this would be t is equal to t0, something. And at finite time, it's even worse. So, like this, like that. Certainly, my results cannot go to such functions, but this is t is equal to capital T. This is my reference solution. Now, I take this reference solution, I type T0. And we know about, from the approximate solution what it is. To leading order, it's the Ausen vortex, making exactly that. Plus, at time T0 is exactly that. Plus order of epsilon square corrections, which are responsible for this not being circle but ellipses. At this time, you take the same initial data and you take the average over the angle. So you take only the radial part, which is this one. Okay? So you take this vortex here and you symmetrize it. So let me try to write a vortex nearby. This one is supposed to be symmetrized. Okay, so it's a little bit far away. I mean, I write it in the function space, not at the same place, because I changed my initial data a little bit by order of epsilon square and by scaling back and forth. And I take this as initial data. And what the statement says is that if you start from here with the initial data, very quickly you go back to the reference solution and you stay close to it up to the end. It is just. And the reason I took this initial data in this form is to be able to compare with some well-defined approximate solution. So this is perfectly defined. I mean, this omega r is defined by a formula. I don't need to compute anything from 0 to t0 to give a meaning to this formula, just an approximation. But the meaning of this is exactly that. So I would like to be able to take initial data which are much further away from that. To have, for instance, a profile which is not exactly Gaussian, but something different, and with larger perturbation. But for the moment, the only thing we can do is that. It's not even expected. Yeah, I mean, the general picture that people expect is you start with something which is, say, a radially symmetric vortex, Rankine vortex, or something like that. Then, if it's not completely symmetric, it will become, no, sorry. You start with radially symmetric. It will get deformed to adapt to the exterior field. And then the radially symmetric part of the profile, which is underlying, if it's not Gaussian, we evolve slowly to Gaussian due to diffusion. So first you adapt yourself to external field, and then there is a relaxation process, a slow relaxation process to the Gaussian, but you are not able to follow the vortices all the way on this process, but we are working on it. I mean, this is something in the air, but for the moment, we'll see that already this operation corresponds in my equation for my W to considering perturbation which are order of 1, which is something we couldn't do so far. Okay. So let me just mention also, this is very quick. Look at this T0 of T to the power of beta. But beta is proportional to delta to the power of minus 1/3. So when delta is sufficiently small, this beta here is 100,000 or whatever you want. So it's the left-hand side here, the right-hand side here will decay rapidly to go towards this solution. And this is due to the enhanced dissipation effect in the vortex core, which I shall explain. So we didn't see it so far explicitly, but now it's 1/3 and whatever. This is enhanced dissipation. Yes?
Do you think it's possible also for a compact definition to obtain the reference of the sky, maybe some very concentrated close to delta or
Yeah.
large close to delta?
In principle, compactly supported initial data are not a problem for Navier-Stokes. People in numerical simulation then take typically a Rankine vortex and look what happens. The process will be more complicated than here, but in principle, conceptually at least, there is no impossibility for that. So let me just mention something. I have to balance my time. Okay, here. You remember exactly the expression of omega r, because omega 0 plus some epsilon square. So if you do that, you see that the left-hand side at time t0 is exactly of order epsilon square. Because the leading term cancels and the first order of epsilon square correction remains. So this is, so initially this is not zero. This is unlike in the previous theorem, this quantity here does not vanish at initial time. It's exactly of size order of epsilon square. And this is what you have in the right-hand side. So if you know that you don't have this term, T0 for capital T, if you take T is equal to T0, this is 1 times epsilon square. Okay, so this is exactly of order epsilon square at initial time. And now what this is doing you is that if T, remark, if T is larger than T0 times 1 plus order of delta 1/3 log of 1 over delta of whatever I want, to the power of 1/2, it means this, okay? So in a time very, very small after T0, T0 times 1 plus something very small, we know one has that T over T0 or T0 over T to the power of beta is less than delta. And therefore, this term is smaller than this one. So everything is at least delta to the power 1/6. And we prefer a nicer power of delta, but for the moment 1/6. And this is much smaller than the epsilon square we had at the beginning. So we have a separation of scale and things like that. We start from here and very close, we are back to the interacting situation. This is a little bit strange because usually enhanced dissipation is to go in the converse direction. You have a radially symmetric vortex, you make a non-radially symmetric perturbation, very rapidly it's axisymmetrized, and you are down to the vortex, like for shear flows and things like that. But here, the reference frame, the equilibrium state is not radially symmetric because of the external field. So if I have something, this is the equilibrium or the metastable equilibrium. I start from this radially symmetric initial data, I'm away from equilibrium, and I am back to equilibrium due to enhanced dissipation in a time which is depending on the viscosity. In the good sense, and the viscosity goes to 0. Okay, so this is the first time I think these estimated enhanced dissipation estimates are used in this context of evolution of relaxation to this interacting state, so on, and I hope they will be used more in the future. So, do you agree a little bit with the statement, or you understand what it means? It's modest in the sense that I would like to take initial data which are further away, but for the moment, let's start with something. So let me show you how to prove this, and the proof is exactly the same as before. You just take the same equation, there is minimal modification. So that's the reason we have this result, because it's easy. So proof of theorem 3 or a sketch of the proof. Step 1. The beginning is exactly the same. You go to the self-linear variable, the same self-linear variable, okay? And you write omega of psi t is equal to omega r. You consider the same approximate solution. This will be our reference solution. Omega r of psi t plus delta times w of psi t. I already recalled this at the beginning of this lecture, so I will not do it another time. The novelty is now that t is larger than t0. Okay? We don't consider this at initial time, but it's only for t larger than t0. The equation for W is unchanged, but since it has disappeared, we will add it again. T dtw plus 1 over delta L W plus 1 over delta the other advection terms, A of W, plus the nominal term which I write B of W, for some obscure reason, is equal to the diffusion operator L of W minus 1 over delta square times the residuum of the approximation. Now, there are a lot of differences with respect to the previous case. The first one is that this is now a well-posed Cauchy problem. Because I have t dt, but it's not a problem because I start at t0. Looks like I'm in t0 dt here. So now I'm not forced to take the Gaussian as initial condition because I can take whatever I want. For some reason, I still take the Gaussian. Okay, but now it's my choice. I was not forced to do it. So I assume that W, so the initial data for W, fine, so initial data, so W of psi 0, that will be a function which I will denote by phi 0 psi, and phi 0 psi is 1. So it's omega 0 of psi, which is the initial data for capital omega, minus omega r, omega r of psi is 0, divided by delta. So it's an explicit function because remember we have an explicit expression. Omega 0 where the leading term is omega r. So it's something like epsilon k, epsilon square omega 2 plus epsilon square omega 3 and so on, divided by delta. This is an excellent function in the Schwarz space with Gaussian decay at infinity. And this phi is of order epsilon 0 square over delta, which is order of t over t0, capital T0. So small t0 over capital T. So in my function space, like y, for instance, this is order of 1 initial data. They were order of epsilon square, but divided by delta. Remember, I write the equation for delta, or for W. Now there is this delta in front. So now I have to consider, instead of 0 initial data, I have to consider initial data which are order of 1, which is a difficulty because I would have the, okay, they can be very small, maybe if I take small t0 less than capital T0, but then this is again cheating like I did yesterday, okay? If I'm in the general case, it is just order of 1, so I should be able to handle this equation with initial data, which are order of 1. So this is the difficulty, whereas, for instance, I have B of WW, this will become large and things like that. I have to handle this one. Okay, so what do? I do another splitting, which is completely trivial. Okay, so it's not going to be disappointed, but okay, that's fine. What do I do now? I will decompose the solution of this equation into 2 parts. One part will take into account the initial data, but only solve a very simple linear equation. And the other one will start with 0 initial data and take care of the rest. Okay, there is other strategy. So further decomposition. This is more or less the last step I want to comment. W of psi T, and write it, and the notation are not Fantastic, my collaborator Martin Donati complains about that. So W0 plus W tilde, where on the one hand, W0 is not the initial data, that's why it's misleading, it's a time dependent function, is the solution of, so I take TDT W tilde plus 1 over delta lambda W tilde is equal to L W tilde, is W tilde. Well, it's 0, sorry, there is 0 everywhere. So. And this is not tilde, so I'm getting tied up again. Let me rewrite this. So what I said is TBT W0 plus 1 over delta lambda W0 is equal to L W0, and W0 at time T0 is the phi 0, so the whole initial data of W. So this is the first problem, obviously a linear one, and W, and this is W0, and now W tilde is the solution of whatever remains. So it will be TDT W tilde plus 1 over delta W tilde plus 1 over delta A of W0 plus W tilde, because the A was not taken into account in the first equation, so I have to take it fully into account in the second one. Otherwise, when I gain the sum of the two equations, I will not recover the correct equation. Plus B of W0 plus W tilde, W0 plus W tilde is equal to L of W tilde minus 1 over delta square times the remainder. The source term also was not taken into account in the first equation. And now W tilde of T0 is 0. So two different problems. The linear one with non-zero initial data, and the non-linear problem here with 0 initial data and all the source term and things like that. So this is the strategy to prove. And what we'll prove is that W0, of course, we start with something which is order of 1.
Yes, sorry. Where does this 1 over tilde come from?
The 1 over what?
1 over delta.
Whether it's not the lambda.
Ah, okay.
There is lambda,
Okay,
lambda,
sorry.
lambda.
Okay.
Both equations have the lambda. Sorry, it isn't my fault. They both have the lambda, and the A and the B are only in the second equation. And if you solve in principle, you should obtain the correct equation. Okay. Now, okay. So the idea is what? The idea is very simple. The first equation, the initial data are order of 1, but they will decay very rapidly to 0 due to enhanced dissipation. So, and then I consider them as source term in the other equation. Of course, these are decoupled, so I can first solve the first one and plug into the second one. Okay, and there will be give small source term in the second equation. So the second equation I will handle by energy estimates and try to prove that it remains small, exactly like the previous argument. Okay. So let me sketch both steps, and then I suppose I will be over. Okay, so step 2, analysis of E and 1 and second. Okay, so what do I do with the analysis of the linear equation? So this is an interesting problem, but it has been solved already. So I can just use the result. So for the analysis of study of the first equation, it's convenient to introduce a logarithmic time. Introduce tau is equal to log of t over t0. Okay. This is very often done in connection with self-similar variable, also to rescale the time into a logarithmic time in such a way that you don't have this TDT. TDT becomes d tau. So the equation becomes autonomous also in the self-similar variable, which is in certain circumstances preferable, okay? This, so this, the inverse is t is equal to t0 exponential of tau. And now the initial data and t0 becomes tau is equal to 0 in the self-similar variable. I couldn't do that in the previous case because small t0 was 0. So if I had introduced this logarithmic time, I would have started from minus infinity to some place, okay, which can be done, of course, but here I start really from 0, so it's very comfortable. So if I make this change of time, this equation becomes t tau is 0 plus 1 over lambda, 1 over delta, sorry, lambda is 0 is equal to L is 0. And this is just an autonomous equation, so you have V0 of tau is equal to exponential the sonic group generated by L minus 1 over delta lambda acting on phi 0. So this is the solution, and this solution can be considered for all positive time because it doesn't depend on the external acting and so on. So this the result I already stated imply in particular that L minus 1 over delta lambda generates a strongly continuous sonic group in the space Y with nice properties. And now you can define this. Okay. Okay, so what can we expect? So we'll have exponential decay in tau. Okay. So remark. Since we know that integral of W0 xi is equal to 0, because initially the initial data have 0 mean. I mean, W has 0 mean initially. So this is preserved by the evolution. We have, let's try the energy estimate. If I make 1/2 E over dt of W0 in my space Y, okay? Y, I remember it was the L2 space with the Gaussian weight e to the psi square over 4, the space in which the operator L and lambda have this nice property. So this is W0 scalar product with e to W0. I replace like this, so it's W0 times L W0 in Y minus 1 over delta W0 with lambda W0 in Y. Lambda is Q symmetric, so the last term is 0. And now you use the fact that L is an operator which is self-adjoint with discrete spectrum, and it has since W has 0 integral, it has no projection on the 0 eigenvalue. So it's this L on this space in this subspace is bounded from above by minus 1/2. So this is less than minus 1/2 W0 Y square. So this gives you the estimate, the cheap estimates that W0 of tau in Y is less than e to the minus 4 over 2 times phi 0 in Y. So that is quite good. If you exponential decay, but this exponential decay in the logarithmic time, it's 1 over square root of t in the ordinary time. And here we claim to have something much stronger, t0 over t to some power which is large, not beta to be 1/2. Okay. If you are happy with beta to be 1/2, you can take this argument maybe, but it's not sufficient. Okay. So let me continue here and keep the theorem. So what do we do? This energy estimate here seems to be optimal, but it is not at all because it does not take into account the mixing effect of the operator lambda. So for this, there is a very beautiful theorem by Perry. Don't give way. And this page on. Done. Which I suppose was published finally in 2020, which tells you that for any phi 0 in the orthogonal of the kernel of lambda, you remember what it was from yesterday. So this is definitely the case of the phi 0 we consider here. We have exponential of L minus 1 over delta lambda. So if I put this code here, no, I forgot this. Okay, that's the code here. Okay, these are some plane acting on phi 0 in y is less than some c0 exponential of minus some small c0 delta to the power minus third, 1/3 phi 0 in y. So you have a decay which is much faster because the decay rate in time, and I forgot the time, usually, okay, that's why I keep clearly, because it's very nice result. So exponential minus C0 delta minus 1/3 to times the norm of phi 0 in y, and this for also. And of course, the constant capital C0 and small c0 do not depend on anything, are just universal constants. So you have an exponential decay, but not with the rate 1/2, with a rate which is the beta that will be in the theorem, and which goes like delta to the power minus 1. Okay, are there experts of shear flows and anticipation in the room? I could try to explain why this delta 1/3 is coming. Okay. If you consider wet flow or this shear flow that we have heard so much in that decay, this will be delta to the power minus 2/3. The scaling of wet flow will be 2/3, and here it's 1/3, which is worse. Why is it so? Because this whole effect is due to what? It's due to, let me draw my picture again, like that. So these are the streamlines of, say, the Lamb-Bose vortex, which is under consideration here. So the free particle run into circles here, okay, and but the velocity field is not constant as a function of the radius. So the angular velocity, for instance, is v divided by r. This is something like has a maximum at the origin and it decays at infinity, like 1/r². So if you take particles which are initially synchronized, they are not synchronized. You have what the physicists call the differential rotation, in the sense that if you take a vortex block here, which is affected by this flow, it gets filamented because different radius rotate at different angular speeds. And this is this variation here. So this is the effect that is exploited to prove an anticipation. The idea is that if you get something, if you take initial data which is not radially symmetric, then you have filamentation and you will create small scale structure with respect to the radial variable. So high frequency in the radial variable, and these high frequencies are then filled by the weak semi-group, and therefore you feel, even though lambda is too symmetric, you feel the action of lambda in the decay of this semi-group. Okay, so this is basically the mechanism. Now it really depends on the fact that the angular velocity is a non-trivial function of the radius. Otherwise, it doesn't work. So if it's a monotonous, I mean, in this region where you have a non-zero derivative here of the angular velocity, so this could be, I don't know, okay. This would give a decay like delta to the minus 2/3, like the wet flow. The wet flow is completely monotone, the derivative has no stagnation point, so you get delta to the minus 2/3. But for a vortex, it's impossible to reach this one, because always at the origin, since the vortex is smooth, you have a degeneracy. So near the origin, you get delta to the power minus 1/2. Okay? Already you cannot go better than delta to the power minus 1/2. This is what you obtain for shear flow when there is a stagnation point of the flow, like quasar or whatever. You get the equivalent of delta to the power minus 1/2. But then you have also what happens at infinity. At infinity, there is no differential rotation at all. So there is no enhanced dissipation effect. So if you work in L2 space or something which is translation invariant, you don't get anything better than this one. Because for data at infinity, you don't fit. But in my case, due to my function space y with this exponentially growing weight, data at infinity do not play any role because they are completely damped by the harmonic oscillator. So somewhere there is a balance between the enhanced dissipation effect that you have in the core and the decay due to the harmonic oscillator you have in the dark field, and the equilibrium somewhere give this delta to the minus 1/3. So this delta to the 1/3 is not a physically well motivated exponent. It relies on to some extent in our choice of measuring in such in the function space Y, which seems natural in the problem, but it's not the only possible one. So altogether, if you want this result to be true for any phi 0 in Y in the orthogonal kernel of lambda, the optimal rate you can have is delta to the 1/3, but it may be for a phi 0 which is given by an explicit formula, we could obtain something better. It's not excluded at all. Okay, but in this in what follows, I will just take for granted the bound by Lee Wei-Zhang and use it for the rest of it. Okay, so this is little remarks in connection with shear flows and integration. So if I have this, okay, so I use this. So I have some immediate corollaries. You will laugh with this corollary because it's not very bien. In particular, you have integral of R2. So this is my W0. So you take W0 of tau in Y square in tau. This is less than constant than delta to the 1/3. This is the origin of the smallness. I mean, if you decay so fast in time, when you take the square, it's the same. You integrate over time, you have delta to the 1/3 that occurs. Okay, so you start with initial data of size 1, but your time life is so small that when you integrate, you obtain something. The L1 norm in time or the L2 norm in time is very small. And this is the effect I will use because they come with a source term in the equation. So they will be small. The small, okay, I said it will be order of 1, but it's not true. They are small when integrated over 1. So the problem is that we would like to have the same result also, not only for the norm of W0, but maybe for the gradient of the norm of W0 multiplied by psi. Remember the kind of estimate we have in the energy estimate. We have to do the energy estimate with the source term. So is it true, for instance, remark, and nearly finished, remark, integral of R2, can we hope something like that for W0 for the gradient of W0? Is it small, this? No, impossible. This is always larger than 1/2 times phi 0 in Y squared. This follows immediately from the energy estimate. You write the energy estimate, you integrate, you take the limit, and you see that this is always. So this norm is small, but with the gradient, it's not small. So whenever I have the gradient, I'm in trouble because it's not a small source term in the L2 sense in time. So I cannot use, so it is useless. This is useful, but this is useless. So now there is another little proposition for our saying it's corollary 1. Now it is corollary 2. It's a little bit more sophisticated. If gamma is larger than 1A, 1 over A, there exists a constant C gamma such that the integral from 0 to infinity of psi W0 of tau in Y square tau is less than constant times delta 1/3 logarithm of 1 over delta times some norm of the initial condition, but I have to put something larger than the norm in Y, so su over psi now 2 E2 gamma psi phi 0 of psi square, and that's it. I hope this is correct. Yeah, I think this is correct. So it tells you the following thing is that you can have an estimate very similar to this one, even with xi. Okay. You should not try to get it from the energy estimate, because from the energy estimate you get nothing. But if you do it in a more clever way, you have the same delta one curve, you lose a log, like we lose a log here. This is one of the reasons we lose this log. And you have to have more decay of the initial data than not just sufficient to be in Y. But this is not a problem for us because our explicit initial data decay much faster. So for us, it's satisfied with any gamma less than 1/4. So it's good. So this estimate tells you that you also have this one. Okay. And now, at least I can array. If you don't know this this for the moment. And I do this one, so this one represents the argument. And now let me finish, just say that everything is okay. So Steven, no analysis of two study of second equation. For the first equation, we have everything what we need. We know that it decays fast, and therefore we have in particular this estimate, this estimate. And now here we do energy estimate. As before. So here you take this equation, and suppose you have you first want to try whether it works for small time, like so you take the energy estimates in the space Y. Okay. So it's interesting because whatever does not contain W0 has already been done. Because the energy estimates that we did so far was for exactly this equation with W0 is equal to 0. So for W tilde, all the energy estimates are already done. So just existing. So you just have to incorporate the contribution from W0 here and here and here. So for instance, here, remember that this A contains differences which are order of epsilon square. Epsilon square over delta is T over T0. You have W0, but you integrate in time in the energy estimate because you consider it as a source term. So you end up with delta to the 1/3. Okay? So this adds a delta to the 1/3 to the energy estimate. And in the non-linearity is the same. So as before, one obtains. Let me write one formula, which will be maybe the last one. Something like a differential inequality. Do I have the differential inequality? Not one, not even. So the energy of W here down to the power 1/2 will be less than a constant times epsilon 5 over delta square plus epsilon square. This was the contribution of the source term that we already had, plus constant here times delta 1/6 log 1 log delta to the power 1/2. So these are contributions which are due to not being apparent here. And these are the contributions, and there is in fact a T over capital P0 in front of all these contributions. This is P0 less than T less than capital. So you obtain for your energy estimate. So either the naive energy estimate if you have a small time, or the more sophisticated, you remember with this weight and so on, you have to do all this with this equation. You obtain the same estimate that you have before, plus in addition a term, which essentially is due to these contributions from the source term. Okay. And then finally, you remember the decomposition we made. So we have delta times the norm of W of tau y is less than delta W. Well, no, it's not. Okay. Here. Okay, fine. Have to be careful because it depends on what I wrote in my note is not completely correct. So finally, to return to this equation, So you have that the norm delta times W of flow in N1. This is finally what I have to estimate because W was my difference between omega and the approximate solution. So this is less than delta times W0 of flow in N1. So plus delta times W kill of flow in N1. This one you use the estimates of Lee Bézin to show that this decays. So this is like, okay, I have delta acting on phi 0, but phi 0 is of order T0, capital T0. So this is altogether of order F-0 square e to the minus 2 times delta to the minus 1/3, something like that. So when brought back to the initial data, this is epsilon square and this T0 of T to the power theta. Exactly. So this comes from, of course, the V0. And this one can be controlled by the energy estimate. This is less than, here again, you have T of T0. So when you multiply by delta T of T0 produce epsilon square, the same epsilon square. And then I add delta to the 1/6 log 1 over delta to the 1/2, which is producing exactly this term. And and this is equal to 1 over gamma integral of omega minus omega r dx up to all these change of variables. So I think this is the end. So I will stop.
So thanks, Thierry, for this last lecture, of course. It's really nice. So, are there any questions?
I see a question over there. Well, I mean, so far, if you analyze this in terms of the equation for this W here, I have initial data for this W which are order of 1, which I could deal easily because the part that comes from the initial data decays rapidly and so on. Okay. I could, if you look at this, okay, I have. Let me write something. Integral, this is to be very precise, that we have to put this phi 0 to solve y squared. Okay, this is the estimate. I took phi 0 over 1, and then I have delta to the 1/3, which taken to the square root was the delta to the 1/6. Now, what I really need is that to be small. So whatever initial data you give me, I think this will be some negative power of delta, which correspond to initial data, which are a little bit further away. So I can, this was not optimal, I don't need to obtain here this delta to the 1/6. If I just want one positive exponent, I can put whatever. I remember phi 0 is disappeared, but phi 0 was omega at T0 minus omega r at T0 divided by delta. This was my phi 0. So whatever has a norm which does not completely kill this delta to the 1/3 is immediately I can take care of this argument. Further away from that, I am in real trouble. I mean, I have to follow something different. I'm afraid that if you really want to start with initial data with a different profile far away, you should be able first to rederive the analog of the Lee-Bézin estimates, but around a profile which is non-Gaussian, and this is a completely open. It's like proving these anticipation estimates or implicit damping estimate for shear flows which are monotone but not wet. This is much more difficult than the wet where you have an explicit formula. Here, the Lee-Bézin argument is very clever, very complicated, and for the moment, it's only for the Gaussian one. So I think we need a more important toolbox if you want to go very far away. So we can improve a little bit, like making it a little bit different, as long as this goes to zero, as delta goes to zero, I will still remain still have some result, but it will not include the data which are very far away. If you take, for instance, the same size, but a completely different profile, this will not work. There will be one over delta, and then this will kill the delta to the one third. So this is very preliminary. It goes into the correct direction, but it's not the final result. I mean, for the starting from the point vortex is close to final form. And we have a precise description of the solution. Starting from more general initial data is just an example.
Okay. If not, we can thank Thierry again.